Hi, hello, mabuhay! Welcome to Cluster 5's presentation of the topic Wave Properties of Light. But before we delve deeper into that, let's have a few background. The wave theory of light was first proposed by Christian Huygens in the 17th century. This theory states that light travels in the form of waves, similar to how sound travels through air. The particle theory of light was further supported by experiments such as the Compton effect. However, the question remained, how can light have both wave-like and particle-like properties? This was answered by the concept of wave-particle duality, which states that all particles, including light, can exhibit both wave-like and particle-like behavior. In summary, the dual nature of light can be explained by the wave-particle duality, where light behaves as both a wave and a particle depending on the experiment being conducted. This concept has revolutionized our understanding of light and has led to many technological advancements. A bit trivia about these people. This is John Joseph Thomson and George Thomson. John Joseph Thomson and George Thomson were two prominent scientists who made groundbreaking discoveries about the atom and the wave properties of an electron. Now let's talk about wave behavior of electrons. Electrons, which are negatively charged subatomic particles, have long been believed to behave like particles, following a specific path and trajectory. But how do these particles behave? Particles in all states of matter are in constant motion, and this is very rapid at room temperature. A rise in temperature increases the kinetic energy and speed of particles. It does not weaken the forces between them. The particles in solids vibrate about fixed positions, even at very low temperatures. However, in the early 20th century, scientists began to question this belief when they observed certain phenomena that could not be explained by the particle model. This led to the development of the wave-particle duality theory, which suggests that particles, including electrons, can also behave like waves. For key evidences that electrons behave like waves, Ellen is ready to take it away.
Here are the key evidences that electrons behave like waves. First is the famous double-slit experiment conducted by Thomas Young in 1801. In this experiment, a beam of light was shown through two narrow slits, creating an interference pattern on a screen behind it. This pattern could only be explained by the interference of waves, suggesting that light behaves like a wave. In the 20th century, this experiment was repeated with electrons, and the same interference pattern was observed. This provided the strong evidence that electrons also have wave-like properties. Second evidence is the Heisenberg uncertainty principle, proposed by Werner Heisenberg in 1927. It also supports the wave-like behavior of electrons. This principle states that it is impossible to know both the position and momentum of a particle with absolute certainty. This is because the act of measuring one property of a particle, such as its position, will inherently change its momentum. This is consistent with the behavior of waves, as they do not have a definite position or momentum, but rather exist as a probability distribution. Another piece of evidence comes from the diffraction of electrons. Similar to how light waves diffract when passing through a narrow slit, electrons also exhibit diffraction patterns when passing through a crystal lattice. This can only be explained by the wave-like behavior of electrons, such as particles would not be able to diffract in this manner. Finally, the development of quantum mechanics, a branch of physics that describes the behavior of particles at the atomic and subatomic level, relies heavily on the wave-particle duality theory. This theory has been successfully used to explain and predict the behavior of electrons in various experiments, further solidifying the idea that electrons behave like waves. In conclusion, there is a wealth of evidence that supports the idea that electrons behave like waves, from the double-slit experiment to the Heisenberg uncertainty principle and the diffraction of electrons. All of these phenomena can only be explained by the wave-like behavior of electrons. This has not only revolutionized our understanding of the behavior of particles, but also has practical applications in fields such as electronics and quantum computing.
Scattering. Scattering is the process where light rays deviate from its path due to non-uniformities in the medium through which they pass.
Finally, the development of quantum mechanics, a branch of physics that describes the behavior of particles at the atomic and subatomic level, relies heavily on the wave-particle duality theory. This theory has been successfully used to explain and predict the behavior of electrons in various experiments, further solidifying the idea that electrons behave like waves. In conclusion, there is a wealth of evidence that supports the idea that electrons behave like waves, from the double-slit experiment to the Heisenberg uncertainty principle and the diffraction of electrons. All of these phenomena can only be explained by the wave-like behavior of electrons. This has not only revolutionized our understanding of the behavior of particles, but also has practical applications in fields such as electronics and quantum computing.
Scattering. Scattering is the process where light rays deviate from its path due to non-uniformities in the medium through which they pass. Uniformities include dust particles, gas molecules, droplets, and etc. So, imagine you're in a room with sunlight streaming through a window. If you've ever seen dust particles floating in the air, you might notice that the sunlight gets scattered by these particles, making the light visible in the air. This scattering of light by dust particles is similar to what happens in the picture, which is called Tyndall scattering. When light encounters tiny particles, it gets bounced around in different directions, making the light visible. So, basically, scattering is when light changes direction because it encounters stuff in its way like dust or gas molecules, and Tyndall scattering is a specific example of this phenomenon. Uniformities include dust particles, gas molecules, droplets, and etc. So, imagine you're in a room with sunlight streaming through a window. If you've ever seen dust particles floating in the air, you might notice that the sunlight gets scattered by these particles, making the light visible in the air. This scattering of light by dust particles is similar to what happens in the picture, which is called Tyndall scattering. When light encounters tiny particles, it gets bounced around in different directions, making the light visible. So, basically, scattering is when light changes direction because it encounters stuff in its way like dust or gas molecules, and Tyndall scattering is a specific example of this phenomenon.
And my part is understanding interference of wave properties. First is introduction. Interference of wave properties is fundamental concept of physics that describe how waves interact with each other when they overlap. This phenomenon plays a crucial role in various aspects of daily lives and scientific understanding from explaining light pattern to optimizing communication system. The definition is interference of wave properties refers to the interaction between waves that result the alterations of their active spaces or both they both overlap in space and time. When waves meet, they can either reinforce in each other, leading to constructive interference or cancel each other out, resulting in destructive interference. We have three applications. The first is optics. In optics, interference patterns help scientists understanding phenomena like the direction and the behavior of light waves passing through different regions. The second application is sound engineering. Musicians and engineering use interference principles to manipulate sound waves, creating effects like reverb or cancelling out on wavelength. The last application is communication system. Understanding interference is crucial in designing efficiency communication systems, such as Wi-Fi network. When minimizing interference ensure better signal quality and reliability. For my conclusion of our part, the concept of interference wave properties is essential for understanding how waves behave when they interact. From explaining patterns of light to optimizing communication system, this phenomenon has research implications across various scientific and technological fields, shaping our understanding of our world around us.
Good day everyone! My name is Jomer Javero and kanina na-discuss na ni Jinky kung ano nga ba talaga ang ibig sabihin ng interference. So, yung interference also occurs between two wave train moving in the same direction but having different wavelengths or frequency. Now, I'd like to provide a situational example. So, when I drop two stone in the water, so yun nga, pag nag-drop ako ng dalawang bato dun sa tubig, yung waves niya is mag-spread out from each stone. So, if mag-overlap sila, makakabuo siya ng interference. So, sometimes, they combined to make bigger waves where they create line up. So, that's on my part. Thank you.
What is diffraction? Diffraction is the bending or spreading out of wave as they encounter an obstacle or aperture. This phenomenon occurs with various types of waves such as light, sound, and water waves. When waves encounter an obstacle or opening, they don't just travel in straight lines. Instead, they bend around edges and spread out. This bending or spreading out results in pattern of alternating light and dark regions, known as diffraction patterns. These patterns depend on factors like the size of the obstacle or aperture and the wavelength of the waves. Diffraction is a fundamental aspect of wave behavior and it's commonly observed in various natural and artificial.
Good afternoon, everyone. My name is Jomar Jovero, and earlier I let the program discuss about diffraction. So, we all know that diffraction is a process in which light ray travels through an obstacle or around a barrier and it's spread out as a result. Now, I'd like to provide a situational example. So, imagine you're in a forest and notice mo how sunlight passes through the leaves, creating a beautiful patterns of light and shadows on the ground. So this happened because or dahil light waves bend around the edges of the leaves. Kaya tinawag itong diffraction. So it's like seeing the nature own light show, and it helps us understand how waves behave when they encounter obstacles. So that's on my part. Thank you.